Thank you for attending this presentation on exploring sustainable CNC model making materials for landscape architecture education. The paper reports on an ongoing research project aimed at identifying, testing, and evaluating alternative CNC model making materials to synthetic foams used by students in landscape architecture programs who are exploring digital fabrication in their academic pursuits. The integration of digital fabrication and computer-aided manufacturing methods has become a fundamental aspect of design education. These methods revolutionize the way students and professionals conceptualize, design, and create physical models of architectural and landscape architectural projects. Methods of making can relate to manufacturing, so things that are additive and subtractive, such as CNC, which we'll talk about today, laser cutting and 3D printing, but they can also be thought of as interactive methods, such as augmented reality sandboxes or clay, more traditionally clay models, which have really strong pedagogical value. CNC milling plays a central role in materializing complex designs with precision and is therefore an important tool for students to master in their time in the academy. It is a particularly valuable process in landscape as it emphasizes slope through a continuous surface rather than contours that you would see in a kind of laser cut stepped model, for instance. However, the prevalent use of polystyrene foam in model making raises environmental concerns, prompting the need for research into alternative methods that align with sustainable design principles. Synthetic organic plastic forms such as polystyrene revolutionized the building industry at the beginning of the 20th century and are now a commonly used building material for thermal insulation. The motivation for this research project arises from a really increasing but also embedded emphasis on sustainability in landscape architecture and the necessity to incorporate eco-friendly practices into design education. Polystyrene, while cost-effective and easy to machine, raises concerns due to its non-biodegradable nature, potential release of hazardous particulate matter when machined, and detrimental impact on our environment. The inherent environmental consciousness of students and educators in landscape architecture highlights the need for alternative materials that not only offer the desired machinability, but also align with sustainability design principles and values that we share. The research project employs a systematic methodology which encompasses material identification, testing, and performance evaluation. To embark on material testing, the project created a list of candidate materials based on an initial review. A range of candidate materials were selected for experimentation, considering their potential suitability for CNC machining based on similar material density properties to that of polystyrene. After a review of terms such as sustainable, green, and environmentally friendly building materials, as well as plant-based and eco-friendly model-making packaging, the study selected cork, recycled cardboard, mycelium, and soap as materials that are overarchingly readily available, lower cost, and renewable. Each selected material contains a unique set of metrics in terms of their color, moisture, density, toxicity, cost, biodegradability, and/or compostability. Of particular note are the metrics of moisture and density in terms of the material's implications for CNC tooling settings. A lack of guiding rules for users introduces uncertainty about process outcomes and really prevents end users from relying on preset tooling selection. For material input, each testing material was cut to a consistent 6-inch by 6-inch by 2-inch tile, and these parameters were selected as a reflection of a standard educational size of polystyrene currently used at the fabrication lab at the University of Washington's College of Built Environments. Polystyrene, in this case XPS, was used as our experiment control. Cork is an increasingly popular and sustainable material due to its unique properties and eco-friendly characteristics. This natural material, harvested from oak trees, cork oak trees, is lightweight, easy to machine, and offers a distinctive texture that can add aesthetic value to CNC milled projects. Additionally, cork's biodegradability aligns with modern environmental concerns, making it an ideal option that is both functional and ecologically responsible. For the purposes of this experiment, 2 types of cork were used. One was a solid piece of cork that was cut to size, which you can see here. And on the previous slide, we had the stacked version that was made up of 6-inch by 6-inch by 1/2-inch tiles. Recycled cardboard is a readily available and cost-effective material. By repurposing cardboard waste, this sustainable, sturdy, and lightweight option not only reduces the environmental impact, but also offers opportunities for further recycling and composting following the life cycle of the project. Its material properties have the potential to offer a unique textured surface. 2 orientations of recycled cardboard were tested, one which was horizontally stacked, which you saw in the previous slide, and the other vertically, which you can see here. Mycelium is a thread-like network of fungal cells, which has gained significant attention as an innovative and sustainable alternative to traditional packaging and insulation materials. Mycelium-based materials are not only renewable and biodegradable, but also lightweight, making them a valuable choice for testing as an eco-conscious alternative. A hemp-based growing kit was used, and the stalk was dehydrated at 150 degrees Fahrenheit, 82 degrees Celsius, for 5 hours. Soap is a biodegradable and non-toxic material that has the potential to be further reused and recycled after initial use, offering students the chance to learn firsthand about material reuse. A clear glycerin melt and pour soap making kit was used by microwaving the kit and casting the liquid glycerin into a 6-inch by 6-inch by 2-inch rubber mold. A Voronoi diagram was selected as an organizational strategy for the testing surface to test the ability of the material to articulate visible patterning as well as variable slope percentages, and this analysis was generated using Landkit's slope pieces, a grasshopper component within a larger landscape architecture specific software toolset for analysis and design in Rhino. With the goal of testing non-standard materials under machining, the primary considerations were how to approach machining speeds and the order of operations. Programming of the CAM operations was done using RhinoCam, a computer-aided manufacturing software plugin for Rhino. When working with polystyrene, its lack of density allows a user to machine the material directly using finishing operations rather than going through an initial roughing pass. With these untested materials, the decision was made to assume a comparable density for material-based feeds and speed calculations to that of MDF. Unlike polystyrene, most materials have a density and hardness that requires multiple passes of machining to achieve the desired product. The CNC-enabled router used in this experiment has a maximum spindle speed of 12,000 RPM. With this limiting factor, the final cut speed of the testing operations was set to 73 inches per minute and a plunge rate of 35 inches per minute. We used a 1/2-inch end mill bit for the roughing pass, and 2 parallel finishing operations were done using a 1/4-inch ball nose bit. A simple wedge-based jig was used to hold the material in position during machining. Between roughing and finishing operations, the bits needed to be changed out, which required a re-zeroing of the zero value on the machining due to the differences in the bit heights. This research project ran 7 milling operations, which tested 5 unique materials. Performance parameters considered during the milling process were time for material preparation, ease of work holding, meaning attaching them securely to the milling bed, ease of waste gathering, potential reuse in addition to post-production considerations of aesthetics, and resolution of topographic expression. As mentioned previously, the first material tested was polystyrene, specifically the XPS, which served as the control for this experiment. Variations of cork, soap, mycelium, and recycled cardboard that we reviewed earlier were tested as potential alternatives against the performance of this control, evaluated here in perspective and plan, as well as the amount of material that's able to be gathered after the milling process. Cork provided the closest replicable final product to our test control of polystyrene by way of model aesthetics. Model resolution was strong for steeper slope topographies, but due to the material color, slopes ranging between 2 to 5 were not easily visible due to a lack of contrast of shading against the material. Cork waste is compostable and easily gathered. Work holding was not an issue due to the density of the material. Preparation time was minimal, requiring approximately an hour of measuring and cutting for solid cork and a 1/2 hour of gluing for the stacked. The largest barrier to cork as an alternative material is its high cost per unit. Both horizontal and vertical recycled cardboard iterations provided fairly poor aesthetic qualities with low resolution in terms of model accuracy reflected in the digital test topography. Work holding was challenging due to the compressibility of the material, especially in the vertical iteration, which caused a milling error. Preparation time for the cardboard involved measuring, cutting, and gluing multiple stacks of cardboard, which was labor-intensive and time-consuming, taking approximately 1.5 hours to prepare per stalk. By contrast, recycled cardboard waste is compostable and easily gathered. The material is free and therefore has a lower unit cost than all other materials tested. Mycelium performed similarly to recycled cardboard in terms of model aesthetics and overall resolution, with the overall topographic information proving difficult to read in the final model. Mycelium waste is compostable and easily gathered, with the potential for reuse and regrowth as future substrate, provided the stalk is not dehydrated in advance of testing. Work holding was not an issue due to the density of the material, though shrinkage of the molded stalk during dehydration did create play in the bed mounting that had to be accounted for. Preparation time was not labor intensive, but took approximately 2 weeks from growth start to milling date. In addition to the potential barrier of material time, cost by way of grow kits could also impact the feasibility of the product, with cost savings improving through economies of scale if implemented at the college level rather than user level. Soap provided the most dynamic aesthetic qualities and a high resolution for model accuracy. Slopes of nearly all levels of steepness are legible and could be further improved through the dyeing of the clear glycerin. An appealing feature of soap as an alternative is its ability for milling waste to be easily gathered and reused. In addition to the reuse of the model material itself, all materials can be heated to liquid form and recast. Due to this, the initial unit cost is negligible, as the material can be reused from one project to another. Soap provides a compelling opportunity to bridge the accuracy of digital fabrication with the human hand to smooth, sculpt, and rebuild or iterate on the model in an analog manner without needing to further use tools for fabrication. The largest barrier to soap as an alternative material was slopes over 50% were susceptible to cracking and breaking off of the model due to the vibration of the machining speed, which could be solved by using lower milling speeds for future tests. The ongoing research project works to raise awareness and generate alternative CNC model making materials for landscape architecture education. As the project continues, it can contribute to the development of guidelines and best practices for landscape architecture educators and students who seek to embrace sustainable and environmentally responsible practices in their digital fabrication endeavors. In addition to the publication of this paper, collaborative efforts with educators will be needed to integrate alternative materials into landscape architecture curricula and assess their suitability for different educational contexts. This research project works to inspire a shift towards more sustainable material practices, equipping the next generation of landscape architects with the knowledge and tools to create a more environmentally conscious and resilient future, both within and outside the academy, and at the scale of model making through to the scale of landscape making. Thank you so much for your time. We look forward to suggestions on other materials for testing, or if you would like to test other materials yourself using the same testing surface, please email us for the G-code.